So in this video, I'm going to show you how to find the flexural properties of a carbon fiber composite shown in the figure. So this is the carbon fiber composite. The width of the carbon fiber is 1.44 inches and the thickness is about 0.21 inches. And using this sample, a smaller coupon is prepared, which is about 0.5 inches wide, and the thickness is kept the same at 0.21 inches, and the length is overall 10 inches. The selection of length for the 3-point bending test depend on various factors, and for that you might have to look into ASTM D7264. The test was conducted using Instron 5567, and this is the 3-point bending fixture. Also, you can use 3-point bending fixture or 4-point bending fixture depending on the requirement. Also, please go back to ASTM again to see 3-point bending test is good for you. For my purpose, I use the span to depth ratio of 1:32. Depth to span ratio of 1:32, and for my sample, the overall span was 6.72 inches, which I rounded up to 6.75 inches. Then on this picture, I don't have the setup for the crosshead, which I have to install it for the test. And the crosshead is centered at the beam span. So for 6.72, you have to check into the ASTM to determine how much the beam should extend from the center of the support. In my case, I was conservative enough to use 10 inches. That left about more than 1.5 inches on both sides of the beam, or both sides of the support. So when I say finding the flexural properties, so there are a few flexural properties that can be determined using the ASTM. And the first goal of mine is to determine maximum strain, which is epsilon, and maximum strain can be determined as epsilon is equal to 6 times delta H over L square. And my next goal is to determine maximum flexural stress. And flexural stress for the procedure 3-point bending test can be determined using the formula 3PL 2BH square. And ultimately, I want to find the modulus of elasticity E, which can be determined as delta stress by delta strain. So H, L, L, B, and H, these are the properties of the coupon. B is the width, S is the thickness, L is the span. The only variables that I don't know is deflection and P, deflection and load. So using the Instron, this device, I can get a curve, something like this, that's going to give me load versus displacement. Upon collection of the data after the test, this is what the data looks like. So I have time, I have displacement, and I have force, right? So I want to use, let's say this is an mm in kilonewton. I want to change that displacement to, let's say, inches, and I want to change the force into lbf. Okay, so this is for one of the sample. I got this in c3.csv. Now the problem with using CSV file is at some point you cannot save some formulas like you would be able to on the spreadsheet. So technically this is not the right way to do. I mean, I can make all the changes formulas, but when I save, I found that most of the time I lose all the formulas. So what I do is I'm just going to keep this data right there. Maybe I'll copy all this data, copy this, and I'm going to go to a new XLSX file, and I'll just copy it over here. So exactly the same formula. I'll just double check if I copied everything. The sum was 3848. I'll go back to the previous file. 3848. So it seems like I double checked and I got all the data that I wanted to. Now I don't have to use this CSV file anymore. I can turn this off. Now this is an mm and this is in kilonewton. I can convert that into inches and lbf, right? So I'm just going to keep the displacement and force to be the same unit, right? So this is displacement, this is force, and to convert this displacement into inches, what I have to do is I got to multiply by that value to mm. So this is going to give me displacement in inches, and for the force I'm going to have to use this formula. So this has to be this one. Now this is in pound force and this is in inches. So I basically want to just copy this and drag this to the end. So what I do is I just press Control and go down, and I have 5226 data. I'll just type something there. I can go up again. I can just copy that, Control C, and go there, paste it all. So now I got all my data in inches and lbf. This is a graph, and I can add data to this. Let's see, what data do I want to add? From here to here and all the way. So it should give me some plot in there. And this one is the force, and this one is displacement. It came in difference. So what I'm going to do is I'm just going to copy this, right? And actually put it over here. So I'll get a single curve, and I can just get rid of that. So you have load on one direction and you have displacement in the other direction. So you can do the proper formatting. I'm just gonna save some time and use the already formatted data that I have. So I'm just gonna take this over here and get rid of this. So for formatting, you can consult any other videos. So let's go back a little bit up And that's it. Okay, so now we wanted to find load versus displacement graph. And from this, now I need to input some variables, right? I need to input some parameters regarding the coupon. So the length of the coupon was 6.7, 6.75, 6.7, let's say 6.7 for now. And thickness of the coupon was 0.203379. And width of the coupon was 0.5085. So that leaves with area equals to that times width times thickness, cross section times thickness, right? Now I can find load at failure, right? Load at failure. Let's say this is the input that I have to fit, right? So these are the inputs that's going to change for other coupons as well. So let's mark it a little different. And load at failure is the same as well. So load at failure for this case is 294.29, 294.29 pound. And strain at failure is the strain corresponding to that 294.29. So that would be, this is actually the displacement. Now what I need to do is I need to find the strain, so I have to plot a different graph. And because this displacement is dependent to the this displacement is necessary to find the strain, let's say in micro strain, okay, micro strain. So from the formula that we defined before, it's going to be 6 times displacement times thickness divided by L power to the 2. And let's put a dollar sign in here because I have to copy them to the overall page. Okay, so basically let's go down there, type something, go up and copy that and paste it over here. So this is in strain. So what I have to do is multiply this by 1,000,000 to find in microstrain. So the result now will be in microstrain. I can copy this graph again, paste it here, and change that displacement to microstrain. So this is microstrain. Now the strain at failure will be that peak, so, and that is shaded with 294.29, so that would be 8891, 8891. So this is the strain at failure. So until now we have determined maximum strain 8891 and maximum load 294.29. Now to determine the modulus of elasticity, you have to find stress when the strain is 1000, and you have to find stress when the strain is 3000. Strain, right? So modulus of elasticity would be stress minus strain, that in bracket divided by 2000, because 3000 minus, let's do this, 3000 minus 1000, right? So that's the formula, and I have to feed this thing with this value manually. Now, from this plot, I don't have the stress yet, right? So all I have is in force. Now I need to find a way to find stress in terms of force, right? So for now, let's just go and determine the force, right? So let's say force from the strain is 1000, force from the strain is 3000. So I can just scroll down. So this is the line for the strain. And when it's 1000, it's 39.16. 39.16, and I'll do the same for 3000. Hundred 4.35. 104.35. Let me double check that again for 1000. $39.16. Okay. Yep. So now what I need to do is I need to find the stress for that. Okay. So the formula for stress is you have to find 3 times load times length, and divided by 2 times width times thickness power to the 2. So that's the stress, and I can copy that formula and paste it over here, but instead of, alright, so let's make sure that this is in KSI as well. Looking at the formula, it seems like it has to be divided by 1000 because the force was in pound. So that's in KSI, and this is divided by 1000 again to get in KSI. And if I'm checking at this formula, this is in microstrain, so I'll multiply that by 10 to the power 6. So this way, so we wanted to get 3 different readings, right? Maximum strain, which is load strain at failure, is 8891. Maximum stress is, so I don't have the maximum stress yet, I'll find that out. And modulus of elasticity is 15,574 KSI, right? So strain is microstrain. So let me go back again. So when you find the modulus of elasticity, this basically means you have to determine the strain, modulus of elasticity based on the strain from 1000 to 3000. So this is the line that you are using. But if you actually extrapolate this looks pretty consistent. So the value you're getting should not be any different, even if you use from 3000 to 5000. But this is just the way ASTM tells you to do. So I think it's better to just go with 1000 to 3000 like ASTM says. Now, to determine the maximum stress, I know the load at failure, right? Load at failure. So what I can do is stress at failure can be, let me just copy this formula because I want to copy at all, but instead of this force, I'm going to use load at failure. Otherwise, the length thickness properties are the same. So stress at failure is 140 KSI. And the modulus of elasticity is 15,574 KSI. And this is the strain. So these are actually the final answer. All right. Thank you so much for listening to me. Have a good one.